Hello, I'm Mike Smayling from Tela Innovations. We've been a member of the EBeam initiative from the beginning. As a charter member, we've been involved in many activities over the years, and today I'd like to talk about some new and exciting activities. You may have read in the press about CEBL, C-E-B-L, or Complementary Electron Beam Lithography. This is an exciting new technology which may help us extend the lithographic roadmap and hence let our industry continue down Moore's Law. Optical lithography has been a very, very strong part of integrated circuit fabrication for the past 50 years. We've benefited from continual improvement through reductions in the wavelength, increases in the numerical aperture, and more recently, resolution enhancement techniques. In spite of all that effort, though, we're limited to a pitch of about 80 nanometers, and we've reached that limit. There's been no new optical capability introduced since 2007. On the other hand, an alternative to optical lithography is EBeam direct writing. Unfortunately, as we've found for many years, that technology is too slow to write the complex two-dimensional patterns used in circuit designs today. In discussions about EBeam lithography, Chris Mack, a year ago in his blog on the Litho Guru, commented on Tennant's law, which says that throughput is related to the resolution to the fifth power. What that means is as we go from one node to the next node, the throughput decreases by a factor of 6. This is really a very serious problem, and as Chris Mack noted in his article, pixel at a time writing simply does not scale and is not economical. In a recent review article, Dr. David Lamb published a revisiting of EBeam lithography in Future Fab, published third quarter last year. In the article, David reviewed the different approaches to EBeam lithography and commented on, again, Tennant's law and its impact on throughput. But in addition to confirming that there's a problem with 2D patterning, David supported the idea of hybrid lithography, which combines EBeam lithography with optical lithography in a format called complementary EBeam lithography. And his conclusion was the value of CEBL is that it complements EBeam lithography and helps enable next generation lithography. We've talked about the problem in lithography and a couple of expert opinions on it. Now let's talk about the solution and see how CEBL fits in. CEBL really requires 3 elements to be successful. One is a 1D gridded design style, which is available from Tela Innovations and has been demonstrated from technology nodes at 90 nanometers all the way down to 12 nanometers. The second part of the solution is optical lithography for lines. The optical lithography may require pitch division to scale the pitch of those lines, and that's been demonstrated on wafers down to 11 nanometer half pitch. So we have the design part, we have the line part from optical lithography. The missing piece is multiple EBeam lithography, the complementary part. That is in development today by several companies such as Multibeam. Let's stop for a minute and look at the process sequence needed to do CEBL. We'll start with one-dimensional lines which are patterned with our optical lithography. These lines can be very uniform, they can have very good process control, and if needed we can use pitch division to get to reduced lines and spaces. These have been demonstrated down to 11 nanometers. Next step is a conventional resist spinning process. We spin resist over the lines. Following that, we go to our patterning equipment, and there's where we'll put the cut pattern into the resist. That, of course, has to be aligned with the line pattern below it. Finally, we'll go to the etching and stripping of the photoresist, which leaves these line segments. These are lines broken by the cuts, which represent the circuit design pattern and replicate what the circuit designer intended in his functional design. Finally, in case you were wondering if this is all slideware and forecasts of the future, since all you've seen so far are cartoons, let me show you some results that have been achieved on wafers and have been presented. These are Sybil results based on single column proof of concept kind of demonstrations. These two examples were presented at SPIE last year at the Advanced Lithography Conference. There are additional papers being presented this year which will show how that's advancing beyond 12 nanometers. In the first example here from Advantest and Tokyo Electron, we're showing an SRAM pattern with half pitch of the lines at 11 nanometers. You can see very good formation of the lines and really excellent results in this wafer SEM photograph of a wafer after etch. In the other example, this was work that we did between Tela and CA Leti. This is showing a random logic pattern done with designs from Tela and patterning at the CA Leti. As you can see, this is a resist pattern. We've got good pattern fidelity and after etch results also looking good. As I said, in addition to these results at SPIE last year, this year at SPIE, we've shown results extending the work to 12 nanometers and below, and certainly we all believe that sub 10 nanometer scaling will certainly be possible in the near future. Thank you for the opportunity to spend a few minutes with you today. I'd like to acknowledge that many of the results here were done in collaboration with other members of the EBeam initiative. Advantest, CA Leti, of course Tela Innovations, and at CA Leti, Vistec equipment was used to do the patterning. So this has been a highly collaborative effort and really an example of how the EBeam initiative brings companies together to get state-of-the-art results.